Hi, we are now going to start Unit 5, which is all about rotation. So let's get right into it. So there are angular counterparts to all of the linear versions of the stuff that we've been learning about so far this year. So linear versions of kinematics, dynamics, energy, and momentum. And that's why this unit is placed where it is right now, because we needed to know all about all those other things in order to apply the rotational counterparts to all these different things. So essentially we'll have things rotating, but apply very similar things. And so we're going to be using Greek variables. So we have theta for our angular displacement. We have omega, this is lowercase omega, for angular velocity. And then alpha for angular acceleration. Make sure your alphas look like alphas and not like a's so that you can keep your variables straight. So a few things are different between linear and rotational. So our variables, as you see, are Greek. And then force and mass have their angular counterparts. And so for force, we are going to be working with torque, and that is symbolized by the Greek symbol tau. And then mass, we are going to be talking about rotational inertia. Rotational inertia, and that is also known as the moment of inertia. We'll be talking a lot more about that, but that is the angular counterpart for mass. Displacement is measured in radians. And as you hopefully know, 2 pi radians is equal to 1 revolution or 1 rotation. And so make sure that whenever you're using any variables, you get it into radians first, and then you can change it later. And so here are all of our variables here, and I'm going to show you how they're going to relate to our linear motion variables. So probably you have seen at one point in your life S equaling arc length. This is also interchangeable with delta x, like in this picture right here. Our delta x is this arc length. And so our arc length is equal to our radius times our angle. And so let's put that over here actually. So radius times theta. And very similarly, our velocity is equal to radius times angular velocity. And acceleration is equal to our radius times angular acceleration. And make sure you keep these straight. These bottom two are on your equation sheet. The top one I don't believe is, but it's very similar. So hopefully that won't be too hard for you to remember. But also you can remember using units, because let's take velocity, for example. We know that velocities, SI units, are meters per second. And so if we have a radius, that is in meters. And then if we have angular velocity, that will be in radians per second. And we know that radians are unitless, and so we end up with meters over seconds, and so that checks out. And so if you ever kind of forget which way this goes, you can use your units to figure that out. All right, so moving on, we have all of our straight line kinematic equations that we've been using all year long. So V equals V naught plus AT. That is going to be, we can use for constant angular acceleration, similar to how when you have constant acceleration, you can use these. Constant angular acceleration, you can use the rotational equivalent. So we'll have omega equals omega naught plus alpha times t. Of course, t is just t, because time is time, whether we're going in a line or rotating. And then the next equation, again, we're just going to be translating or shifting to all of our rotational variables. So I'll have delta theta equals omega naught t plus 1/2 alpha t squared. And the last one, we have omega squared equals omega naught squared plus 2 alpha delta theta. And so let's do a problem where we're going to be using this. So we have a turntable capable of angularly accelerating 12 radians per second squared, needs to be given an initial angular velocity if we want it to rotate through 400 radians in 6 seconds. What must its initial angular velocity be? So for this type of problem, same thing as when we were doing kinematics, we're just going to do our if that. Write that out. I personally like to be more specific with my variables, so I'll write omega naught, omega final, delta theta, alpha, and time. Just because we're starting with these new rotational ones, I want to make sure that we know exactly what we're talking about with all of these, but you do whatever makes the most sense for you. So let's stick these all in. So I have 12 radians per second squared. That is my angular acceleration. Radians per second squared. We want to know initial angular velocity. So this is our question mark. We have 400 radians. So that is our delta theta. And then 6 seconds. So very similarly, we look at what we have. I have these. I want to know this. I don't care about my final angular velocity. So I look at my equations. And for this particular case, this middle one makes the most sense because there's no final angular velocity there. So let's write that out. So I have delta theta equals omega naught t plus 1/2 alpha t squared. And we can just plug things in here. So I'll have 400 equals omega naught times 6 plus 1/2, what's my angular acceleration? 12 times 6 squared. And if we work that out, if you do the math, we're going to find out that our omega naught equals to 30.6 radians per second. And cool, so we got it, we're done. Let's look at the next problem. It says how many revolutions has the object made? Let's switch colors since we're switching problems. And so revolutions is like how many times has it gone around. We are already told that it goes through a net 400 radians. So we almost have our answer, except it didn't want to know radians, it wanted to know revolutions. So we will convert that. So radians, I would like radians to cancel out. I would like to end up with revolutions. So there's 1 revolution for every 2 pi radians. So we can just do that division problem and find out that we have 63.7 revolutions. And we're done with that. All right, let's do another one. So this is going to be a non-uniform angular acceleration. We're going to have the first part where it's one thing, the second part where it's another thing. If you are feeling a little confident, I would recommend pause your video right now and see if you can get it, and I will just continue to work it out. You can fast forward to the answer when you get there. Okay, pause. All right, let's continue. So, teenager puts her bike on its back and starts the rear wheel spinning from rest to a final angular velocity of 250 RPMs in 5 seconds. So I already don't like the RPMs. Let's fix that. So I have 250 revolutions per minute. I don't really want minutes. And I do want seconds. So 1 minute for every 60 seconds. I don't want revolutions, and I do want radians. So there's 2 pi radians for every 1 revolution. So 250 divided by 60 multiplied by 2 pi. What do we get? We get 26.18 radians per second. Cool. So now we at least have the right numbers here. We want to calculate our angular acceleration. So let's go back to blue. Oh, we're blue, even though it didn't look like it. Okay, so we are going to make another if dat. So I'll make mine with my specific variables. Let's see, delta theta, alpha time. So let's see, we have a final angular velocity of our 26.18 radians per second. It started from rest, so we start at 0. We want to know, oh, and it goes for 5 seconds. And we want to know the angular acceleration. And so if I have initial and final angular velocity, I have my time, I want to know my acceleration. Again, you can look up at your equations and figure out which one makes the most sense. I hope you will agree with me that omega equals omega naught plus alpha t makes the most sense. So I have 26.18 equals 0 plus alpha times 5. And so if we plug this in, I find out that my alpha is 5.24 radians per second squared. So we got that part. Cool. Yay, part B. Now she's going to slam on the brakes. Okay, let's change colors for that. Let's be green. Okay, she slams on the brakes, causing angular acceleration of negative 87.3 radians per second squared. How long does it take? All right, let's do another if dot. Omega naught, omega final, delta theta, alpha time. So our initial angular velocity is going to be what we're ending with over here because it was spinning. Now she's slamming on the brakes. So that final is going to be the same thing as this initial. So I can plug that in. So 26.18 radians per second. If she's slamming on the brakes, so she's coming to a stop, then our final is going to be 0. What else do we know? Oh, we know our angular acceleration is negative 87 point. Oh gosh, sorry. Please ignore that. We don't care. Negative 87.3 radians per second squared. And we want to know how long. So these are the same variables we were dealing with before. We're going to use the same equation. So we have omega equals omega naught plus alpha t. So we have 0 equals 26.18 plus negative 87.3. And we want to know our time. Yeah, cool. That looks good. All right, so if we work this out, our time is going to end up equaling about 0.3. It's 0.299 seconds. And so that is our final answer for part B. And then if I want to know how many total revolutions has a wheel turned from the time it starts to at rest to the time it stopped again. So essentially we have to do the blue part and the green part, figure out our delta theta, and then convert it to revolutions. And so the equation that I'm going to use for both of those, I'm not going to work out all the math for you, but I will show you the answers. So I'm going to, for both equations, I'm going to use delta theta equals omega naught t plus 1/2 at squared. And so for the first part, I'm going to plug in all of these blue variables over here, and I'm going to find out that my delta theta for that first part, when she spins it up and it gets to the high speed, is going to be 65.44 radians. And when I do it for the second part, I'll make it green so it's more clear. I'm going to use that same equation for all the green variables, and that second part is going to be 3.925 radians. And so since I was speeding up the first part, slowing down the next part, I would just add both of those together. And we end up with 69.4 radians. And then if I divide that by 2 pi, just to get my revolutions, we end up with about 11 revolutions. So hopefully if you work with that math, you will get the same thing too. Okay, let's move on. Let's go back to black. All right, so rotational mass and force have new definitions for rotational motion. We talked about this a little bit in the beginning. And so for mass, the rotational equivalent is going to be the moment of inertia. Moment of inertia, also called rotational inertia. And the units for this are going to be kilogram meter squared. And we're going to be talking a lot more about this going forward, how to calculate it, whether it's constant or not, or there's all sorts of things, but just get that in your head. And then instead of forces, which were in newtons, we're going to have torque, which is in Newton meters. All right, so let's talk a little bit more about torque right now. So two things. So if I have a wrench right here, your axis of rotation is, as you would imagine, where you are rotating it around to the place that stays still. And your radius is the distance from the axis of rotation to the place that the force is applied. And then your force is whatever you're pushing with. And so two things required to have a non-zero torque. Thing number one, force must be applied at an angle, meaning that if I take that wrench and I'm pushing directly on the wrench, like with a 0-degree angle, that is not going to move my wrench at all. Same thing with a door. If you push on like the side of a door, it doesn't open it. You have to like push at an angle, and then that is going to be creating a rotation. So at an angle from the point of rotation. And then also force must be non-zero. So if these are true, then you will have a non-zero torque. And torque is a cross product. So torque tau equals R cross F. And like we said earlier, the units are Newton meters. And hopefully you remember from some math class, but your cross product would be the first thing cross the second thing. So in this case, R cross F, which would be RF sine theta. And this gives you the magnitude. If you want to know the direction, you would use the right hand rule. So in this case, you put your right hand, oh, of course, it's the right hand rule. Be really careful. If you're right-handed, you are often writing with your right hand, and then you think about the right hand rule, but this is your left hand. So please use your right hand. So you put your fingers in the direction of R, or in this picture right here, I put it in the direction of A, and then you curl them towards B, or if we're doing torque, it's R, and then curl towards F, and then your thumb would be the direction of your vector, of your torque vector. And so as we go on, and it's perpendicular to both A and B, or both R and F. Here's a fancy little picture showing you a little bit more about how to do your right hand rule. We can talk more about that in class if you guys have any questions, but just so that you guys know what we're going to be doing, if your thumb, when you're doing it, is either going up or it's coming out of the board, we're going to consider that positive. So let's write that down. So thumb up or out of board is positive. And then similarly, if your thumb is down or into the board, it is negative. Okay, cool. So we're gonna rank these torques. I'm gonna label them each so we know what we're talking about. Oh goodness, it just moved. All right, come on back. So we have torque 1, torque 2, torque 3, and torque 4. Let's work them out. So for number 1, my radius is right here. So again, we're gonna have R, F, sine theta for all of these. So my radius for this one is 4. My force is 40 newtons. If I right hand rule that, I'm going to be going R, F. So my thumb's coming out of the board. So that's positive. And it's sine, the angle between those two is 90. So again, that's just 1. So 4 times 40, we will get 160 Newton meters. If we do this second vector right here, then our radius is just this. That's just 1. And then 1 meter. Okay, let's put our units up here. So meters there, newtons there. And then our force, I kind of covered it up a little bit, so sorry about that. That's 20 newtons. And our angle is 60 degrees. So times sine of 60. So sine of 60 is 0.5. So 1 times 20 times 0.5 equals 10 Newton meters. Cool. Let's do the third one. My radius from 0 to 5 is going to be 5. You might be like -5, but no, we're already taking into account our positive negative with our right hand rule. Oh, I don't know if I did the right hand rule for the second one, but again, I would go up, over, coming out of the board, still positive. Third one, over, down, still coming out of the board, so still positive. So I have 5 times 30 times sine of 53. You can see that since your angle's right there, if you do the sine of that, it will be giving you the perpendicular component, which is exactly what you want. If you feel more comfortable getting your angle in here, which would what be sine 127, you'll still get the same component. It's going to be the same either way. So same answer. And you'll end up with 120 Newton meters. And then for a fourth one, down here, our radius is 3, but if I right hand rule that guy, I go down and over, it's going into the paper. So that's going to be -20. And then my sine of 90 still, so just times 1. So I'll have -60 Newton meters for that one. All right, a little bit more. We have, if I wanted to get the net torque on this system, I would look at my radius 1 times torque 1. I see that's going back into the board, so I would have negative R1 T1, and then I look at my R2, that's coming out at me, so that's positive, so plus R2 T2. We got that. All right. Last little bit, conditions for static equilibrium is that my net force is 0 and my net torque is 0. So this is how we're going to be dealing with rotations. So as long as everything equals 0, then we can make an equation with our forces or with our torques, and we can find out a lot of information about that. So suppose, where's my elephant? Do I have a picture? My elephant fell off. You should have an elephant on your paper. So I have an elephant right here. That's my elephant. And it's 4,600 kilograms. So my F1 would be 4,600 times 10. I have a fulcrum right here, and I have a mouse over here. F2, the force for my mouse, is 0.025 kilograms times 10. I'm using 10 for gravity right here. And so if this distance right here is 10 meters, I want to know how far away does my mouse need to be. And so the sum of my torques would be from my fulcrum, because that is going to be my axis of rotation. For my elephant and my force 1, that's going to be coming out at me, so that's positive. So I have 4,600 times 10. This is my force. And then times 10 meters, that's my radius. But then for my mouse, my radius and then force is going to go into the board. So minus, I'm just going to multiply these together right now. So 0.25 times x. And if I work this out, I find out that my x, how far the mouse needs to be, is 1,840,000 meters away from the fulcrum in order for the elephant and the mouse to balance. So that is it. All done. Goodbye.